Today on the drawing board by Talbot Pie, we talk about everyone's favorite burrowing creature, the mole. Oh wait, no, not that kind of mole. Like the spy mole. Wait, no, wrong sheet of paper. Yeah, we're talking about the best mole, the chemistry mole. Today on the drawing board, we talk about moles and chemical equations. So this magical mole, what is it? Well, it represents the number of atoms in a unit, which we decided to call the mole, which is abbreviated MOL instead of MOLE. We decided on the number 6.022 times 10 to the 23rd atoms per mole. So where did that come from? That's a good question, really. Just some guys a long time ago decided on it. They said it had to do with the molar mass of hydrogen being 1 gram per mole, or per 6.022 times 10 to the 23rd atoms. But the problem is, hydrogen is actually 1.01 grams per mole, so I guess it didn't come from there either. No one really knows anymore. So a mole is really big. Like, it is bigger than any of us can even fathom, really. In fact, a mole is so big that if we had a mole of basketballs, it would be as big as the moon. Like, if you received a mole of pennies on the day you were born, and then you spent $1 million for every single second of your life until you died at 100, you'd still have 99.99% of your money in the bank. And heck, if you wanted a mole of turkeys, you could go around and form 16 Earths. So yeah, we could say a mole is pretty big. So why do we care about moles, really? Well, one of the biggest things we use with moles is we will use it to find the molar mass. So what is that molar mass? We use it in chemistry a lot in order to convert between the number of atoms we have of something and the actual weight we have of something. So the units for molar mass most commonly are in grams per mole. You'll notice that moles of mass for a specific substance is always going to be the same. So for example, for hydrogen, it is always 1.01 grams per mole. This doesn't depend on anything. We can change the pressure, it'll still be that. We can change the temperature, it's still 1.01 grams per mole. That's the same for carbon at 12.01, for oxygen at 16.0. In every atom you can think of, its molar mass will never change. So some of you might be thinking that you've seen these numbers before. You've seen hydrogen that has 1.01 next to it and a carbon that has 12.01. Well, that goes back to the periodic table. When you look on the periodic table, you have your little boxes for each element, right? So let's say we had hydrogen over here. It's the first on atomic number. And of course, down here is where we see that number 1.01. So on the periodic table, what on the bottom there is called the molecular weight. That's also known as the molar mass. If you go back to one of our older videos, which we will link somewhere on the page here, we've already talked a whole lot about the periodic table, where these sit on here, so check that out if you want more information on that. Now, one thing they'll tell you on the periodic table, they'll tell you that molecular weight number, so for hydrogen that's 1.01, they're going to say that's in a unit called AMU. This stands for atomic mass units. But the cool thing about AMU is it is pretty much the same as grams per mole. We just sometimes we'll use AMU when we're talking about just a specific atom, but we'll use grams per mole when we're looking to convert between things. So essentially they're the same thing, just sometimes they have different names. So now that we know about moles and molar masses, what do we do with them? Well, often we'll use it to find the weight of a compound. So for example, we have this compound here. It's made up of lead, chromium, and oxygen. So to get started, what we're going to want to do is to find the molar masses of each of our individual atoms here. So I went ahead and looked these up on the periodic table. For lead, we have 207.2 grams per mole. For chromium, we have 51.996 grams per mole. And finally, for oxygen, we have 16 grams per mole even. Technically 16.002, but we won't worry too much about sig figs. So now that we've found those, the next thing we're going to want to do is start applying these numbers to these molar masses. So let's start with this little piece inside the parentheses here, Cr2O7. So we'll start with chromium, so that would be Cr2. So to get that, we're just going to take 2, multiply it by our molar mass, 51.996, and we are going to get 103.992 grams per mole. Perfect. So now let's do oxygen, same exact thing. So it's O7. So we're going to take our oxygen, which is 16, and we're going to multiply that by 7, which is going to give us 112 grams per mole. So that's what is inside the parenthesis here. Next, let's apply this subscript outside. So since there's a 2 out here, that means this whole thing inside is going to be multiplied by 2. So the easiest way to do that is start by just connecting these two numbers right here. So we're just going to add those together. So if we have Tr2O7, that is going to be 103.992 plus 112. When we do that, real quickly, we get 215.992 grams per mole. So now let's apply that subscript. In order to do that, we're just going to multiply that number we just got by 2. Pretty easy. So we're just going to take 215.992, multiply that by 2, and we will get 431.984 grams per mole. There's one last step we have to do here, and that's of course add in that lead at the beginning, and we're going to do that exactly how you think. We're going to take what we already had and just add that last lead in there. So overall, for PbCr2O7, we are going to take our molar mass of lead, which is 207.2, add on our right half there, so that's 431.984, to give us a final answer of 639.184 grams per mole. So what does that number mean, 639.184 grams per mole? That means if we have 1 mole of this substance, we will have 639 grams of it. It's a nice way for us to convert between grams and moles within larger problems. So since we said molar mass doesn't change based on any properties, it makes it pretty simple to tackle a problem kind of like this. So in this problem, we want to know the mass, the molar mass in grams of compound C. The problem is we don't know what compound C is, but we are told both the reactants, and we know the formula that 1 of reactant A plus 1 of reactant B will form 1 of reactant C and nothing else. So even though when you actually do this equation, you get a really weird product that looks like that, yeah, we don't need to worry about that here. We can do it just based on what we know about these 2 reactants and the chemical formula. So let's look at reactant A here. First thing, let's count up the carbons. So 1, 2, 3, 4, 5, 6. So we can say that is C6. So nothing else here other than hydrogen, so let's go on to those. So since this only has 1 bond, it's safe to say there's 3 hydrogens. 1 here, 1 here, 1 here. So this carbon right here has 3 bonds to it, so it'll have 1 hydrogen. This one also has 3 bonds, so it'll have 1. Same thing here, and same thing here. This one at the end is like that one, so this guy will have 3 hydrogens on it. Count those guys up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this compound is C6H10. So let's go over to this one now. So first we'll count the carbons, 1, 2, 3, and 4. So we have C4. All right, next let's do these oxygens, 2 of those, easy. And then we'll do the hydrogens. Same thing as we did last time. 1 bond to this carbon, so 3 hydrogens. 2 bonds to this guy, so 2 hydrogens. This one has all 4 bonds, so it doesn't get any. Oxygen, of course, doesn't get any in this situation. And we put a hydrogen there, there, and there for this last guy. So counting those up, 1, 2, 3, 4, 5, 6, 7, 8. C4O2H8. Usually this would be written C4H8O2. So now that we know those, and we know the chemical formula from up here, we know that these 2 just get added together to form our last compound. So we can just add up our carbons, 6 plus 4, so C10. Hydrogens, 10 plus 8, it's 18. And no oxygens here, 2 oxygens here, O2. So that is the formula of our last compound, and that is all we need to solve the rest of this problem. Okay, so more paper, transferred the only thing over we need, which is that formula. So now we'll do the exact same thing that we did in the last problem. So go to our periodic table, we can find our atomic weights. So for carbon, that's 12.01, hydrogen, that's 1.01, and oxygen, that is 16. We'll now apply the subscripts to each one, just like we did last time. So C10 is 120.1, H18 is 18.18, and O2 is 32. And of course, at the end, we're just going to add those all up to get our final compound. So when we put those all together, we get a total of 170.28 grams per mole. And that's it. So now that we have that answer, we're done. And as you can see, we take that really big, ugly reaction like that, and we can get an answer to this just by knowing what the reaction does instead of needing to deal with that big, giant, ugly thing. So in that last problem, we got to look at another new concept, a chemical equation. There we had 1A plus 1B forms 1C. And that is, in the simplest form, a chemical equation. Now, usually what we'll see is something more like 1 CO2 plus 1 H2 forms 1 CO2H2, or something like that. That's just a hypothetical example here. But often these chemical equations are a tool we'll use along with things like molar mass to solve bigger, more complicated problems like we did in that last one, but they get even more complicated from there. So understanding what these are and how to balance these equations is really a key part of understanding chemistry as a whole. So if we take a look at a simple equation here, so we'll say N2, that's just nitrogen, plus H2, that is just basic hydrogen, and that will form NH3. This is one of those quintessential reactions in chemistry that has done so much for us just as a society as a whole. So this is a very important reaction, and luckily also a very easy one to balance. So we're looking to balance equations. First thing we're going to want to do when we're looking at this problem is looking at how many of each atom we have on both sides. So let's do a count of both sides. So on this side we have N2, so that means we have 2 nitrogen. We also have H2 on this side, so that is 2 hydrogen. That's it on that side. On this side, let's do the same thing. So we have N, just 1, so it's just 1 nitrogen. Then we have H3, so we have 3 hydrogen. Easy as that, we've counted both sides. Now what we want to do is we want to try to make each one of these numbers match. So we want to make the coefficient in front of the N on the left match the right, and same for the hydrogen. We have 2 on this side, 3 on this side. So neither of those balance right now. We're going to try to fix that by adding coefficients in front of each of these terms. So the first thing we're going to want to do when we're looking to balance is choose where to start. You generally want to start with the atom you have the least of. So in this case, that would be our 1 nitrogen on the right side. So since we know we need 2, what we should do is we'll take this NH3 right here, this ammonia, and we'll put a 2 in front of it as a coefficient. So now, instead of having 1 nitrogen, we have 2 nitrogen. And instead of having 3 hydrogen, we have 6 hydrogen. So what's cool about that is now our nitrogen is completely balanced. 2 nitrogen, 2 nitrogen. We are all good to go there. So now let's take a look at hydrogen. So we have 2 hydrogen on this side and 6 hydrogen on this side. Well, unfortunately, that is not balanced yet. But the good news for us is that's easy to fix. So since we get to 6 and we're at 2, what we can do is we'll put a coefficient of 3 in front of our hydrogen term. So now instead of having 2 hydrogen, this side goes to 3 times 2. We will have 6 hydrogen. And of course, 6 hydrogen on this side matches with 6 hydrogen on that side. So we have a fully balanced equation because 2 nitrogen, 6 hydrogen, 6 hydrogen. And that's it. That equation is balanced. So we have 1 N2 plus 3 H2 forms 2 NH3 or ammonia. So now let's do a problem that combines both the molar mass stuff that we learned about earlier and the chemical formula stuff we just learned about. So we have a sample of a compound consisting of 141.99 grams of carbon, 10.23 grams of hydrogen, 27.97 grams of oxygen, and this is combusted to form CO2 and water. So the question is asking us to identify the empirical formula of the compound, then to balance the chemical equation for the reaction containing the new compound. So this is really 2 parts. Part A is identifying the empirical formula of the compound, and then part B is balancing the chemical equation. So we'll take this one at a time. Part A. So we have carbon at 141.99 grams, oxygen at 27.97 grams, and we have hydrogen at 10.23 grams. So now we're going to take all these and convert them from grams into moles, because we can only find a chemical equation if we have it in moles. We'll go back to our periodic table and find our molar masses. So for every 1 mole of carbon, we are going to have 12.01 grams. Down here for oxygen, same thing. 1 mole of oxygen, we're going to have 16 grams. And down here for hydrogen, same thing. 1 mole of hydrogen is 1.01 grams. We'll do a little division here. I know, no one loves division. I don't either. That's why I did it ahead of time. You get 11.8 here, 1.68 here, and 10.1 here. So we're being asked to find an empirical formula. So in order to do that, the easiest way is to take our smallest number, which in this case is 1.68, and divide all of these by that number. This by 1.68, this by 1.68, and the 10.1 by 1.68. So once we do that, we're going to get a new set of numbers. This will become 7.02, this will become 1, and finally this will become 6.01. Now we take a little creative liberty being chemists, and we're going to say 7.02, it's close enough to 7, 6.01, close enough to 6, and with that, we have essentially just written ourselves our formula. So we'll take our carbon, since we have 7 of those, we're going to make this C7. Then we'll go to our hydrogen, so we have 6 here, so we'll have H6. And then finally we'll go to our oxygen, we have 1, and that is our empirical formula and the answer to part A. All right, so that's part A. So let's move on to part B. So now we want to find the chemical equation for the reaction containing this new compound. So we know the reaction, told us that above. So it's our compound, C7H6O plus O2. It's going to yield CO2 and H2O. So the first thing we're going to want to do on this problem then is probably balance our carbons. It's easy to see why, because we have one carbon-containing compound over here, one over here, plus we only have one carbon total on this side, so it makes it a good place to start our balance. So on the left side here, we have 7 carbons, C7, and nothing in the oxygen compound. Over here, this is our only carbon. There's only one of them, so we're going to need 7 of this compound. So when we go over here, we're going to have 7 carbons equals 7 carbons, and with that, we are good to go on our carbons. Okay, let's move to our next easiest compound. In this case, that would be hydrogen. Since it's only one compound on this side, one compound on this side, makes our lives way easier. So on this side, we have 6 hydrogens. On this side, we have 2, so 6 is not equal to. So since this side has less, we can multiply this H2O by 3. That'll give us 6 hydrogens on the left from there. And it'll give us 3 times 2 is 6 hydrogens here, meaning we are now good on hydrogens. So now let's go on to the tricky one, and that's our oxygen. So let's look at what we have right now. So on the left side, we have 1 plus 2, so that's 3 oxygen over here. And over here, we have 2 times 7, that's 14 oxygen, and another 3 over here, giving us a total of 17 oxygen. Well, that's a bit of a problem. 17 and 3 aren't equal. We can't change anything on the right side anymore. Those are already set in place. I mean, we can change them, but then we got to rebalance everything. So let's see if we can just change on the left to match on the right. So what if we change this first compound? Let's say we just even put a 2 here. Well, if we put a 2 here, we now have twice as many carbons, which would screw up our balance over here, and we'd have to completely reset. So let's ignore this compound and just look at our O2. So we need to go from 3 oxygens to 17. So since we're getting 1 from here, that means we would need to get 16 oxygens from this guy. Well, fortunately, since it's an O2, we can do that. If you just put an 8 here, that means we're now getting 16 oxygens from this plus the 1 from this. So 1 plus 16, that gives us 17 oxygens on this side, 17 on that side. That is balanced, and we can say our entire equation is balanced. So our final answer for part B is 1 C7H6O plus 8 O2 gives us 7 CO2 and 3 waters. And guess what, guys? That's it. Problem's done, and that is it for us here today. So a quick little summary of what we've learned. So first, a mole is 6.022 times 10 to the 23rd of anything. Doesn't have to be atoms, although when we talk about it in a chemistry standpoint, we do talk of atoms. An AMU is equal to grams per mole in most cases, and you'll find those numbers as the molecular weights on the periodic table. Again, go check out our other video for more on that. Molar mass is a great thing for when we want to know the mass of a substance, and we know the number of atoms, and it's what allows us to switch back and forth between the two. We also learned about chemical equations and how A plus B forms C plus D. And of course, when we are balancing these, we want to balance individual atoms instead of balancing molecules. And with that, we'll be able to balance a whole equation, and you can do even more things and just keep adding them to your chemistry toolbox. That's it for us. I'm Chris with Drawing Board by Tau Beta Pi. Thanks for watching.